Hi, we are continuing our development of shear force and bending moment diagrams. Our new problem is a cantilever beam with a distributed load and an end concentrated load like shown here. We have already done this problem for finding out reaction forces and finding out shear force and bending moment at particular locations. Now we are going to do shear force and bending moment diagrams. So let me just make sure that we are on the right page by reminding you that the slope of shear force diagram equal to the distributed load. The slope of bending moment diagram equals the shear force diagram. Jumps in shear force equal to concentrated load, and upward concentrated loads give me positive jumps. Jumps in bending moment diagram equal to concentrated moment, and in this case clockwise is positive, counterclockwise is negative. Okay, so remember that. Clockwise is positive, counterclockwise is negative. Even when I said it, I wrote the wrong thing. I'm so used to writing clockwise positive. So please remember, the sign conventions are really critical for us to get this thing sorted out straight. So that's the shear force, that's the bending moment diagram. So what we are going to do is, first step, we draw the axis as usual. Second step, find reaction forces. And moments. Then step 3, draw the load picture, draw the full FPD with all forces shown. And that's going to look like this. Let's start up here and go all the way like that. And because I will need it later, I'm going to try and grab it. Forget that. We'll redraw it. Don't worry. So then we have a concentrated load here. That's the external reaction, 18. Then we have a counterclockwise bending moment here that goes like that, and that will be 27 kilonewton meter. Then there is this distributed load that goes halfway along the beam, and that is 8 kilonewton per meter. And then there is the external load here, 6 kilonewtons. Okay, so now we are going to draw the shear force diagram for this. As usual, we redraw the, it's again convenient to do this in a grid paper so that your dimensions are right. And then we mark these points by drawing parallel lines like that, so that it is easy to see. And then our first step, we are going to draw the shear force diagram, and we're going to start here and we're going to go up 18. I'm going to go up 9 because I'm going to assume each unit is 2. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I go up 9. I'm going to draw that in blue. So you can see I went up 9. That's this guy. Then this says go down by 8 kilonewton for every meter. This is a downward slope. Remember, the slope of this figure is that figure. So we are going to go by a downward slope. How far should I go? The area of this thing will tell me. So I'm going to draw, notice that I have to go down. And if I compute the area of this, area will be 8 times 1.5, that is 12. So what I mean is, after 18, I have to come down 12. That means I'm left with 6. That's up to this point. That is 12. That's the area. So 1, 2, 3. So I'm going to go down like a straight line like that. The slope of this is minus 8. That's that color. Okay, I come down 12. This height is 6. This total height is 18. Then I'm going to go flat like that all the way, and then I jump down by another 6. That's that guy. Okay. So just to make sure, we will need this information. The area of this will be 18 plus 6 over 2 times 1.5, which is 24, 12 times 1.5. That's 9 plus 3, 12. 12 times 1.5 is 12. 12 plus 6 is 18 units. 18 kilonewton meter here. So we will use that. And the area of this is 6 times 1.5, which is 9 kilonewton meter. So we will need these areas so that it's convenient for us to do the next one, which is the bending moment diagram. So since we already know that we will need lots of space, so I'm leaving myself some space here, and I want to draw the bending moment diagram here. Okay, as usual, that's the initial location, that's the final location, this is the point of the jump. So first thing we notice is that unlike all the previous cases, there is the concentrated moment, and it is 27, and it is counterclockwise. So remember, concentrated counterclockwise external moments are negative jumps. So I go up here and I jump down by 27. So I want to keep like maybe 3 per unit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 3s are 27. So I'm going to go down here like this. This is 27 units. And then I land up by adding this much area to this minus 27. So I'm going to take that, add it to this, and I say, okay, when I come here, it will be minus 27 plus 18, which is minus 9. 1, 2, 3. So this is 18 units. That's this area. Okay, so I know where these 2 points are. And I know that the third point, minus 9, this area is plus 9, so I land up with 0. So I know there's 3 points. Now the question is, can I draw the curve? Notice that since the slope of this curve is that curve, you see that the slope is not constant, it's a straight line. So the curve will be a parabola. So then there are lots of possibilities which way the parabola is to be. So we will figure that out. Notice that the first point that you realize is that this jump is 18. So the initial slope is 18. So it's going to look like that. The final slope is 6. So that's going to look like this. That's a slope of 6. And let me redraw this 18 slope properly so that I can draw. So what will happen is, my parabola is going to look very shallow, but it's going to look something like this. It looks almost like a straight line in this graph. That's because my parabola drawing skills are terrible, but you can see that it's a parabola that looks like this. How do I know that it's not a parabola that looks like this, but a parabola that looks like that? Well, first thing is, this slope is 18, that slope is 6. The second thing is, if you go up here, you can see that the load curve gives me curvature. So you can see that the curvature says go down, go down, go down. So the curvature is negative, or it tells me that the parabola is pointed downwards. You can just look at the load diagram and you can figure out that the parabola is pointed downwards. That is, it's concave downwards. So that's the shape. And then from there it's a straight line all the way here. Why is it a straight line? Because slope is 0. Okay, and you can see curvature is 0. Okay, I'm sorry, slope is 6, curvature is 0, so that's a straight line. So just to remind you, this gives you a parabola pointed down. This gives you a straight line of slope 6. This is initial slope, final slope, this allows you to compute the values. Okay, so that's our story. So this is our final graph, a parabola in the beginning followed by a straight line. Okay, and it looks pretty similar because of the size of these things. It's a very shallow parabola. It's almost a straight line parabola. Okay, with that we are done.